All right. Smelled like what? Well, I wish. I ought to just go ahead and give them to you with the grades that are on there. Well, I'm looking for a curve.
Did you staple the drop form on them? And with your signature?
All right. We're going to start looking for deflections of structures. With any luck at all, I've told you enough times what you're going to use them for. You're going to use them to solve for forces in statically indeterminate structures, and why statically indeterminate structures are far superior to determinate structures when you can cost effectively build them. One of the ways is to use work and energy. The method here is called real work, because you really do put a real load on the structure in the direction that you're looking for the answer, and they know that for sure is a 2. It's got to be a 2. Adams, how big is it? Get her number and let's get on with it here. 979-846-1 something. Come on, man. Here he is blabbing your ear off while you're trying to learn. I'm trying to embarrass him. Why were your lips moving? Oh, I'm sorry. Plumber, for crying out loud. All right, so we're going to use real work to solve for these deflections. If you put a real load on a structure, in deflecting the structure, it will do some work on the structure. That work will be stored as energy inside of the structure, and we can equate the two and solve for the deflection caused on the structure. As an example, here's how much energy is stored in a bar. We'll use this one for trusses. Put a force F on a length of a bar, dx. The amount of energy stored in there will be the average force times how much deflection you get on the bar. It's simply the area under the curve. But you have an equation from 305 for how much deflection you get on a structure when you load it axially. PL over AE. In our case, P is the load F. The length is dx, whatever the area is and whatever E is. Then there's a little bit of energy stored in a little piece of a loaded bar, axially loaded. Would be equal to F over 2 times delta, which is F squared dx over 2AE. And if you want the total amount of energy stored in that bar, then you integrate F squared dx over 2AE. In most bars, F is constant along the length of the bar. The area is probably constant inside of that bar, and it's probably made out of one material. If it's not, you'll have to leave these numbers underneath the integral sign. But in most trusses, these are constant. You simply integrate dx from 0 to L, and you have how much energy you store in a bar with an axial load on it. Now that's if the load is a real load that caused these deflections, namely one that starts off at 0 and gradually increases in intensity until it reaches some level that you have set. Restrictions are no fair yanking the load on there at high rates of speed, no fair putting energy in there other than just barely loading the bar until it reaches the maximum load that you're going to reach. If, on the other hand, you had a bar and it already had a load on it, this load, and it has already deformed, and I don't know about it and don't care about it, But then you come along and you put a load on it. Let me call this maybe a lowercase f to distinguish it. You came along and put a force on the bar. Now then, this little piece of load here that was already on there before I got here, I didn't know you had that on there. When you pull and deform the bar, rather than having this guy's piece of energy be a 1/2, he starts off with a full F and he ends up with the full F, and therefore the energy that he puts in the bar would be F times how long the bar gets. This we'll use right away. This is like if you put a unit load or a 1 kip load on a structure somewhere for some purposes before I get here, and then you put the real loads on the structure. If, on the other hand, you have a piece of a beam that you bend, I'll go ahead and just lock down one side of it, then it will cause a rotation of the face, and you will store energy in the beam. This one was when your mom used to take a rubber band and stretch it and pop you with it when you were bad. That's that energy. Here's where she takes a ruler and she bends it and makes you put your hand on the desk, and the ruler looks like this, and here are your fingers. You know what's coming. That energy has been stored in that ruler in bending. Here's how much energy you store. The energy stored will be the magnitude of the moment times the angle that it rotates the face through. It starts off at 0. It reaches a maximum of whatever m is, and therefore, again, the average moment through the angle of rotation theta will be the energy stored. So d theta is, if you remember from my guest a couple of days ago, d theta dx is equal to m over ei. This is the equation that d squared y dx squared integrated one time. D theta is equal to m dx over ei can substitute back in d theta. And this is a little piece of energy and a little piece of beam, like this was a little piece of energy and a little piece of a bar. It's equal to m over 2 times d theta, m dx over ei. And so it has a very similar form to the axial load. As opposed to an F, you have an M, and opposed to an EA, which is the linear stiffness, you have a rotational stiffness, EI. Now, both of these, you may very well have more than one of them, so that the total energy in the whole thing would equal to the sum of all of the little individual bars in the truss, if there's more than one, and the same way here. The energy stored in the structure, because you load it, you may have to integrate between 0 and L for several members. And not only that, you may find, even more likely in this case, that the moment does not remain constant, and you'll have to write equations that cover the entire length of each member and do all of the members. So total would be the sum of all of the individual members. He didn't even stay, did he? I mean, the other people at least had the courtesy to walk out while I was walking in, but... All right. Well, we're not going to do it right now, but that's just to remind me to do it. Because some of these ne'er-do-wells may come back. I don't know. We'll see. All right. Now, for example, for a truss. Again, the real work done on the truss will be the load that you put on it. times the deflection over 2, average load, and the total energy will be the sum of F sub I, L sub I, A sub I, E sub I for all of the members. For beams, you're going to have the same idea as you do for a truss. Here's a load P. It causes a deflection delta. The load P started off at 0. It increased gradually until it reached the full intensity of P, at which time delta was the deflection. The work that you did to get the beam deflected was P delta over 2, and the energy stored in a beam will be m squared dx over 2EI. So here's an example, page 369 in your book. He wants to use the method of real work to determine the deflection of this bar in the x direction due to a 30 kip load in the x direction. Now that is fortuitous that he wants the horizontal deflection and not the vertical deflection, because this force isn't pointing in the downward direction, and so I wouldn't be able to tell you that the energy that this guy caused was 30 times this deflection because it's not pointed the right way. I can only tell you that the energy, the work done on the truss will be half of this number, the average force, times this deflection, because the force was going that way and the deflection is that way. So right off the bat, you see a serious limitation on this method. If he had asked me for the up and down deflection, I don't have ways, but real work won't work because you don't have a force going in that direction. Not only that, real work won't work if you had another load in the vertical direction. Just say you had 60 kips. Because as this load pulls this thing to the right, this point goes down. And I got how much work, like 30 cut in half times delta x, and I have a 60 cut in half times a delta y, but I don't know who to split up. I don't know what part of it is delta x and what part of it is delta y. So the limitation on this method, powerful as it is you can only have one load on the structure, and you can only answer the question, what is the deflection of the structure in the direction that you applied the load? Here's our basic equation. We say that the work done on the structure is the average force times how far the structure deflected in the x direction, and it's equal to the sum of, let's see if that equation is right, F squared L over 2AE, F squared L over 2AE. Now, he's already done most of the work for you. Don't anticipate this will be the case on your homework. You put a 30 kip load on here and you sum moments about point A. You sum moments about A is equal to 0, is 30 times 20 minus this guy times 15. I'm going to mark that as a known number. You sum forces in the horizontal direction, plus 30 to the right. This is a roller. 30 to the left. I'm going to mark that as a known number. And then some of the forces vertical, I'll mark that as a known number. All right. I got a keeper. No. Yeah. You're pretty astute. That's because Getman followed the same path you followed, except he turned right. Bummer. All right. Now, with these forces, this 30 kip load goes right into this member. I'm going to mark that as a known force in the member. Some of the forces horizontal for this joint right here would be plus 30 minus this force in this member times its angle, and I can solve for the force in this member. Knowing the force in this member, I can sum forces vertical and solve for the force in this member. And that's what we did on the quiz, and I assume you know how to do that. I'm going to list the tension numbers as a positive and the compression numbers as negative. That's equal to, you have to go get the force in the member times the length of the member divided by 2 times the area of that member times divided by the E of that member. According to this guy, the areas of all of them are 2.4 square inches and E is 30. F squared, this is for member AB. Here's the force, 50 kips squared. It's a plus squared times the length of the member is 25 feet, changed into inches, divided by 2 times the cross-sectional area, divided by the modulus of elasticity. To that, you have some energy that got stored in bar 40 kips, BC. So this is for member BC. How much energy got stored in that member was F squared L over 2AE. The force is negative 40 kips, 20 feet long, 2, area is the same, E is the same. Plus, this is for member AC. Incidentally, any members that have no force in them will come out with no contribution to the deflection. Here's his force, minus 30 squared. Length is 15 feet long, divided by 2AE. Solve for delta. It's only one unknown in the equation, 6/10 of an inch. Pretty nice, works pretty well. If, for example, you had the same structure and you wanted to know the vertical deflection of that point, and if the real load on the structure were 10 kips, then you would do the same thing. You would solve for the forces in the members, get the reactions first, then solve for the forces in the members, and you would set P times its deflection in the vertical direction is all you can solve for, sad to say. Cut in half, P delta over 2, equal to F squared L over 2AE plus F squared L over 2AE plus F squared L over 2AE. You'd actually find in this case that this is a minus 10 for this guy. That guy's a 0 and that guy's a 0. And when you worked it out, you'd find that it's equal to PL over AE, because all the load goes right into the vertical member. All right, here's one for bending. I have a concentrated load on the end of a cantilever beam. That's nice, because the load's going the way I want to find the deflection. The equation for moment at any point, calling this x, would be P times x. The work that you will do on this structure is the average force, P over 2 times delta. That's how hard you'll have to work to get that thing deflected, some delta. The energy stored in it is equal to, make sure I got that right, energy stored in a beam is the sum, there's only one beam in our case, integral of m squared dx over 2ei, integral of m squared dx over 2ei. It's equal to the integral from 0 to L. The moment is P times x, so that's P squared x squared, dx over 2ei. The load can come out, the 2ei can come out. Integral of x squared is x cubed over 3 from 0 to L. Is equal to P squared L cubed over 6ei. setting how hard you worked to make it deflect, equal to the energy you stored in the beam, and assuming you didn't hit it real hard and cause it to vibrate into waves, in which case you'll have to take a vibrations class. P delta over 2 is equal to P squared L cubed over 6EI. The deflection is equal to PL cubed over 3EI. For simple cases, works out nicely. Wouldn't work well for this case. Wouldn't work for that guy. You could try to solve for the deflection under here, but when you did, you wouldn't have the fact that this guy also put some energy and bent the beam before you put that load on there. And there's no way around that using real work. So, as you might imagine, we got a way around that too. Too much stuff here to copy it all down in notes, so I'm just going to steal it right out of the book. Page 370 in your text. Follow along, because this gets kind of interesting. We use a thing called virtual work as opposed to real work. What it does is it puts a unit load on the structure before you get there, which causes some things to happen. Then, and you put the unit load at the point where you want the answer, in the direction that you want the answer. And then, and admittedly, it probably deflects a little bit, not enough to matter. We'll make this 1/1,000,000th of a gram. And then you come along and you put the real loads on the structure. At that time, your unit load will go along for a free ride, full intensity. And then the load P will also deflect something. Knowing that this guy is on there for the full time, full blast 1, and the deflection that we're looking for, this times this has got some energy, you'll find that additional energy is stored in this beam. And you'll be able to get it back out so that you can find the deflection underneath that load. Now, they usually call this make sure what this guy does. Got a dummy load, reaction in furnace is the Q system. So for example, if you have a beam or if you have a truss, you'll go ask the boss, where do you want the answer? He says L over 2. You say, what direction? He'll say up and down. You'll go put a unit load on the structure and just arbitrarily give it the name Q. There's some energy going to be associated with this when this one bends. Then, with that in place, you separately put the load P, normally called the P system, and you solve for energy and work done. And this is what you do for trusses. I'm going to tell you that the work done in a system of loads Q is equal to the energy stored in the system due to the load Q. Going to have a 1-bar truss shown on the next page. I'm going to tell you that I know things like how long, if you put the real loads on a structure, will they get? And if you put some real loads on a structure, how much work would they cause? Here's what we're going to do. First, we're going to put some P loads on a structure. This one will just have one bar. If they have multiple bars, you have to do this a bunch of times. Before the load, it sits AB, and after you apply the load, it gets longer and it moves in the direction of the load P, but unfortunately somebody else has got a force on it, which is causing some energy to be stored in it, or if it doesn't move, then there won't be any energy stored due to that load. It gets longer, delta L, and I'm going to tell you that the amount of work done on the bar is equal to P times movement is delta P, and call that WP. This force here, because it rolled and didn't move, that's free. It didn't add any energy to the bar. Now then, looking at the bar itself, I don't know what this force is and don't really care right now. I'll ask you what it is once you get a real structure going. You'll have this force will elongate the bar an amount delta L sub P. And therefore the energy that you stored inside of the bar is equal to 1/2 of the force times the elongation. The energy that you stored in here is 1/2 of the load that you applied times the deflection. The energy that you stored is 1/2 of the force in the member itself. Good morning. Times how much you stretched it. That's work done on, and this is energy stored in. Now then, I'm going to separate the unit load out and put it on there only as opposed to the real loads. Call it a Q load. It'll be 1 when we get going because it's convenient to stick a 1 on there. If you stick a load on here, the same thing happens. The Q loads will cause a deformation, a rolling of this member. It will cause an elongation of this member, and you'll have the same idea. The work done on the bar is this guy times this guy, force through distance. Average force will be cut in half. This guy right here, because he rolled in a horizontal distance, didn't go up and down, so it didn't add any, didn't cost you any work to do that. When you pull the thing longer, it got delta LQ, and some force was generated inside of the member. Half of this force, average of that force, times how long it stretched, delta LQ, is equal to how much energy you stored in the bar due to the Q loads. You okay? All right. Finally, I'm going to put them both on there at the same time. In other words, I'm going to show you a picture that's got Q and P, and obviously by superposition, it has to total out to what you had here plus what you had here. Here is how, when you put the Q load on first, here's how much energy you put in the bar, work you did on the bar. And then when you came and added a second force, this force P now starts at this elevation, this level, because you already got a force on there. You add WP, where the first little piece is the same. Here you see it's Q times delta Q. Now then we start putting the real loads on the structure after we've already applied the unit load, or the Q loads, and you pick up this much energy. Get that on there all at the same time. It is P times delta P cut in half. Here is P. Here is your deflection due to the real loads, cut in half. But the total force you've put on there requires the area under the curve to be the sum of everything. And the reason is this white missing piece here is because when you walked up on it, it already had the unit load on it, or the Q load on it. And when you stretched it some more, he went along for a free ride. And therefore you pick up this much energy, work, that you had to do to the structure to deflect it. It's very similar to this. Here's a spring. It was used in your BB gun. If they leave the spring uncompressed when they install it, and they ask you to compress it, here's how much energy you will store in the spring available for shooting a bird. This much. Half of P times delta. To get you some more energy with the same spring, what they do is they pre-compress it. They pre-compress it to this point where you've already got a force P on it, or some force, whatever they decide to preload it to, and then they come along with you with a little pump bar, and they tell you to add your force P on top of this spring. At that point, here's what happens. You started off with this force. The minute you try and pump the thing, you feel the spring's kind of tight, and you now bring it up to this level. Here's how much work you did to the spring. The work you did was your force, 1/2 times the distance of travel that you compressed the spring. But because the guy pre-compressed the spring, you pick up this much additional work required, and therefore total energy available to shoot the BB at the gun is a starting number plus your number. It's a lot more energy. That's exactly what's happening here. When you put the load Q on there, even if it's only 1 ounce, when you put the real load on there, added, that unit load or that Q load travels through a distance and causes this thing to raise up such that this is how much energy, how much work you did on the spring or on the bar. Now then, how much energy is stored in the spring or in the bar? Well, I know how much energy was stored in there just because of the Q forces. That's the 1/2 of the force Q times the deflection, the change in length Q. And I know you have this much, but to add on the top of it, but because you're starting at this point, this guy again, you have to, in other words, once you finally say the force is Q plus P, I've got to have a Q plus P on this side. And then for the deflection, I've got deflections that are due to the unit loads or the Q loads. Then I have deflections due to the P loads. Then I have changes in length and changes in length. Now you already told me that this guy was equal to this guy, so this part here has to equal to this part here. That's what we said, 1/2 of Q times delta Q, 1/2 of Q times delta Q is equal to 1/2 of the Q force times the change in length due to the Q force. Here's the F sub Q, here's the delta L sub Q, and the same values for this guy. Then I can tell you that W sub Q has got to equal to U sub Q. The little area under this one has to equal to the little area under this one, because you already took these two pieces as equal and those two pieces as equal. Now W sub Q is Q times the deflection due to the real loads, and U is F sub Q, that's the force inside of the member, times the change in L due to the loads P. Now then, this is where I'm so far. W sub Q is equal to U sub Q. W sub Q is equal to Q times delta P. There's Q times delta P. That's this guy. And U sub Q is equal to F sub Q delta L sub P. So that's where we're at. That says, give me a Q load. We're going to probably make it a 1 for convenience. Times how much does the real load move is equal to the forces due to the Q loads in the structure times how long the real loads cause the member to get. Now that takes some thinking, but if you'll notice, we got something that we're really looking for here. That's this guy here. Putting summation signs on them if you have more than one member. I'll ask you to sum up any Q forces you have. Generally speaking, you probably only need one. Truth is, you can put several on there and get some good information out of them. Times the deflection caused by the real loads. This will be, of course, in the direction that you put the unit load, is equal to the summation of all of the forces in the members times how long or what change in length did the real members undergo because you loaded them. And this number here, of course, is change in L sub P for any one of the members would be the force in that member times the length of that member divided by AE. So with the summation sign on them, the sum of the Q forces times the deflection at P, this is really the guy we're looking for, is equal to the sum of all the forces in the structure due to the Q loads times the real load distortion. Oh, it's so quiet. You say, yeah. Show me how you use it. Well, here's how you use it. Basically, you've got a structure. You have a 30 kip load on it. You'd like to know the deflection in the X direction. You could get that answer out of using real work, because it just so happens the deflection you're looking for is in the direction of the applied load. But instead, I can put a set of Q forces on there, which I'll conveniently show as a 1 kip load. He shows this is a dashed arrow because it's not there yet. And in fact, none of the numbers he shows you in the structure are influenced by that 30 kip load. But he puts that on there first, then he adds the 30 kip load on there, and he uses the equation that the sum of the Q loads, they're 1, and there's only one of them, times the deflection due to the real loads in the direction of the unit load that you put is equal to the sum of all the forces in the members due to the Q loads and the corresponding PL over AE due to the real loads. So here's what I'm going to do. First, I'm going to put a 30 kip load on here. This is the P system. Going to sum moments about A. 30 times 16 minus something times 12 is equal to a reaction, 40 kips. Sum of the forces vertical, now that's known. Sum of the forces horizontal, now that is known. Cut out a joint, solve for the force in the member Baker Charlie. The real force in the real member due to the real loads is equal to 40 kips of compression. That's why I list it as a minus. In real work, you didn't have to be real careful. If you got the force wrong, no big deal. You just square it anyway. Now then, it matters. What did I do with that list of names? It's too comfy, too sleepy. There he is. There he is. Sum of the forces horizontal, minus 30, plus this guy's horizontal component is equal to 0. This guy's horizontal component is 30. Once you multiply the force in the member times the cosine of that angle, you find out that this guy has 50 kips of tensile force. That's why it's called a positive. Here's your P system. That's who does this stuff right here. A lot of times the book will call it due to the real loads. That's also the guy who does this. That's due to the real loads. Secondly, I'm going to take the 30 off and I'm going to put a unit load on there. 1 kip load. I'm just wondering here. I've forgotten to tell you the truth. I believe, strictly speaking, it's a little nicer if you don't put a 1 kip load on there, but if you just put a 1 on there. We'll see. This guy, of course, has the unit of minus 40 kips. I'm going to put a unit load on there. Some moments about point A, 1 times 16 minus this reaction times 12. Solve for the reaction. Turns out to be 4/3 of 4/3. Some forces vertical, plus 4/3 minus 4/3. Plus 1 to the right, minus 1 to the left. Now I have the reactions. Knowing the reactions, I can solve for the forces in the member using method of joints or any other method that you know. Some forces horizontal is equal to plus 1 minus this guy's component, gives me 5/3 tension. And sum of the forces vertical gives me 4/3 compression. So the truth is I didn't need to solve for those reactions to get the forces in those members. And now that I think about it, I really didn't need these reactions to get the forces in these members. All I had to do was cut out a joint at B and put it in equilibrium, and I'd have had those forces. Now then, here is the result. The result is you multiply your dummy loads or your Q loads or your unit loads, whatever you call them, times the deflection due to the real loads in the direction of the unit load, and set it equal to the sum of all the forces due to the Q loads times all the forces due to the P loads, the dummies and the real, times L over AE. 1 kip, I really think that 1 probably goes away, times delta in the x direction, and that is the deflection at the unit load. That deflection is not set by this real load. When you put the unit load on there, you must put the load at the point you want the deflection, in the direction you think the deflection goes, and then if it comes out a negative number, you'll know you guessed the deflection's direction wrong. Is equal to, here's our Q load, 5/3. Here's our P load, 50 plus, 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 plus. 5/3 times 50, the rest of it is over 2, times the length is 20 times 12 over 2 for the area, E for the 30,000. Then you get some deflection due to the 4/3 in this member and the minus 40 in that member. There's your minus 4/3, there's your minus 40. L over AE, L over AE, 1/2 inch. But here's what you can do. You say, well, I did that before. I don't say I gained any ground. When the boss asks you how much it moves in the y direction, now you're ready to go. All you do is you come and you put a unit load in the direction that the boss wanted to know the answer. And he doesn't know if it's up or down, and you probably don't know if it's up or down. Looks like from the sketch it's down, but who cares? You guess it's down, and if it comes out plus, you're right. It went down. Here's your Q system. This is the Q system. Here is a Q1 system. Here's a Q2 system. It's used for finding another deflection. One kip down, draw a free body of that joint right there, take that 30 kips off of there. That's only what we're really doing. We really put the unit load on there, and then we put the real loads on there. But without that, sum of the forces vertical is equal to 0. That's 1 kip of compression. And sum of the forces horizontal is equal to 0. That's 0 kips of force in that member due to this loading. And you just simply reevaluate the same equation. You multiply your 1 times delta y is equal to, and you sum up all of the P system, Q system combinations, L over EA. First, this guy here has a Q of -1. There he is. This guy here has a force of -40. There he is. That is across a length of member 16 by 12. The area is 2. E is 30,000 plus. Now then we go for this second member. The Q in that member is 0. And therefore the contribution of this term will be 0. The answer comes out when you solve for delta y, 0.128 inches. Now let me check something here, because I've forgotten. Yeah, he's okay with that. You can use a kip. Here's the reason why. If you use a 1 kip load on this side, you write down the kip. And the force caused inside the member will now be 1 minus 1 kip. And that kip cancels that kip, and the remaining numbers will give you inches. I was thinking that it seemed like we used to just put a 1 on there. Well, that works too, because if you just put a 1 without a kip, then you get a load in here that's a 1 without a kip, and this guy doesn't have a kip, and that guy doesn't have a kip. So it really doesn't matter. Checking the units, this 40 was 40 kips. This force was depends. Let me put the 1 kip back on there. On this side is a kip times delta, and on this side is a kip, and the force in the member was a kip, and the length was in inches, and the area was in inches squared, and the E was a kip per square inch, puts it upstairs. And so we had a kip times delta is equal to kip inches squared over inches squared kip. So a kip canceled a kip, and a kip canceled a kip, and an inches squared canceled an inches squared, and it left us with inches. And if you're an old timer and your prof told you that that ought to just be a 1 instead of a 1 kip, you wouldn't have that kip and you wouldn't have that kip, and it still turns out fine. It turns out fine. All right, read this stuff. Good stuff. General information. Here's one that's more complicated. Phooey. He's been listening. He's probably been listening the whole time. Kruger. Mr. Kruger, not this problem that's stated, but if I wanted to solve for the vertical deflection at B for this structure as loaded, what would you do with your unit load? Let me repeat because the question got a little long. If you wanted to solve for B vertical for this guy right here, how he's loaded, what would you do with the unit load? Number one, where would you put it? And number two, which way would you show it? Good. That's exactly what you do. If somebody asks you on this structure, if you wanted to know what this load and this reaction did to that structure in moving this point up and down, you would come in here and you'd put a downward unit load. One kip, take a choice. You would solve for the forces inside of these members. This would be your Q system. Here would be your P system. And you would use the equation. Just like that. It says, please multiply your Q loads times the deflection at the point you're interested in due to the real loads in the direction you put your unit load. There's a lot of words go right in here. Set them equal to the sum of all the forces that you find in the truss due to Q. Here they are. And as a matter of fact, this would be 0, 0, 0, 0, and this would be 1, and it would be a minus 1. Let me get rid of all these P load things we have. You'd multiply individually this guy times this guy plus this guy times this guy. Oh, heavens. How long has that been going on? Here was his answer. His answer was put a unit load down at the point you want the answer. 1. Causes, actually just goes right on through to the reaction. 0 forces in the members. You'd multiply this guy times that guy, L over AE. You'd add this guy times that guy and get nothing. You'd add this guy and this guy to get nothing, and you'd add this guy times that guy and get nothing. And then you'd add a minus 1 and a minus 60 times a minus 60, L over AE. Here's what he asked. He says, I have a structure truly loaded as shown. 60 kips out on the end of this truss. Cross-sectional area of everything is 4 square inches. E for all of the steel is 30,000. Howdy.
Howdy.
So he doesn't, like Getman, he could care less, man. He'll walk right out the door and not care. But everybody else is a little too shy to do that. This is the Q system. He set it up in a table form, which is kind of nice. He has member AB. He has solved for the forces due to a unit load in the horizontal direction at B, because the boss asked you for the horizontal deflection at point B. You get 0 force in these members because there's no load out here. Cut the joint out and solve for the forces in the members. Then put the load on here, cut this joint out. Sum of the forces horizontal is equal to 1, so that's 1 to the right, 1 to the left, so I agree with that number. Sum of the forces vertical is equal to 0, that's why that's 0. 1 to the right, 1 to the left. Cut this joint here, right here out. Sum forces vertical will tell you this guy here. Sum forces vertical is equal to minus 3/4 plus the compressive force in this member times the slope of this guy. Slope of this guy is 15 by 20 by 25. And solve for the force in the member. So he writes down, for each of the members, here are the forces. AB, BC, CD, AD, and BD. 1, 0, 0, minus 5 force, 0. Then he writes down the forces due to the real loads. 80, 100, minus 80, 80, 100, minus 80, minus 100, minus 60, minus 100, minus 60. Then he writes down the length. He's going to get his answer in feet here as opposed to inches, and that's okay. 20 feet, the lengths of each member. Here's the cross-sectional area of each member. He told us that 2 of the bars had a 5 square inch area. Everybody else had 4. The 2 bars are Alpha Dog, Baker Charlie. Alpha Dog is this guy, Baker Charlie is this guy. That's why you got a 5 here and a 5 here. Everybody else is 4. And here is your Q load force, real load P load force, L over A, and he didn't bother putting in the E. He'll probably put in the E just before he hands the answer to the boss and puts a box around it. He just didn't want to carry the E with him. Everything else changed, so he didn't have any choice. He couldn't leave them out and just put it in later. So, setting your 1 kip load times the deflection in the horizontal direction at joint B equal to, here's your sum. There's your sum of all of the numbers that you got. 1025 times 12, and then he divided by E. Now let me see here. This was in feet, so he multiplied by 12 inches in a foot. So now he's back in inches. Should have gone ahead and put 20 times 12 in here. There's certainly nothing wrong with what he did, but if you forget to do that, you're toast. All right. Now let's try one that's just made up out of nowhere. Here's a truss. Well, every time I add a bar, of course, it causes more calculations. Here it is loaded with 300 kips. I'll give you the reactions. 100 kips on this end, 200 kips on that end. Here's A, B, C, D, E, F, G, H. I want to know the horizontal deflection at D. Now, no question about it, 90% of the work on this method, and there isn't any better method and no quicker method, is going to be solving for all of these forces. Dimensions, 15, 20, and of course 25 across the diagonal. Any of them that we can just stick the force in there, let's just do it. Otherwise, we got to solve for them. 0, 0. How? Well, I drew joint D in my head and put a force in the member there due to the real loads and said no way. Because some of the forces horizontal has to equal 0. This guy doesn't have any horizontal component. This guy's got no vertical component, 0. Force in member Baker-George plus 100. Why? If you want the force in member Baker-George, you cut through member Baker-George, cut through the structure. Sum forces vertical equals to 0. You got the force in that member. Balances this reaction is 100. What's the force in this member right here? First off, let me go back and fix my signs here. I remember our signs are tension is plus. If this guy pushes up, what does this force have to do to that joint? Push down. Our sign convention we've started with, we are going to live with it. That's a negative because it's a compressive force. Now, what's the force in that member? 200. That's a positive 200. What's the force in this member? 100. So a lot of these, they don't take a lot of time. It's pushing on the joint, therefore the member's pushing down on the joint in compression. It's a minus 100. Any more you see are easy to get? Hg, all right, is equal to what? It is indeed. You take this joint right here out. Sum forces horizontal, good, is 0. All right, now then they're getting a little more to them. This guy here, if you sum forces vertical on a cut that looks like that, these two people won't help you hold this thing up. Therefore, his vertical component must be tension, must be pulling, and his vertical component must be 100. And if you say, well, I'd rather draw a free body, I don't blame you. There's the free body. This is 100. Here's the force in member AB. Here's the force in member AG. It's sitting at a slope 15 by 20 by 25. And here's the force in member HG, which is 0. Well, G will come out of that pencil in a minute, or there we go. Sum of the forces in the vertical direction is equal to 0 is equal to plus 100 minus AG times, not all of AG points down, only 15 out of 25 points down. And therefore AG is equal to 166.7 or something. Thank you. Okay. Don't need too much accuracy. And it is a tension force, so I'll go list it as a positive 166.7. And I'll go list it as a 166.7. I hope you see why. If you cut that one and his vertical has to balance 100 and nothing new has come in, then his vertical, when he's cut, has to balance the 100. I can some moments, let me move HG's name out of the way here. I can sum moments about point G to solve for AB, or I can cut out joint A and sum forces horizontal, either one. The sum moments about G is equal to 0 is equal to 100 times his moment arm, 20, minus AB times his moment arm, 15. AB is equal to how much?
Is that 100 times 20 negative?
It is minus. Yes, thank you. Thank you. I like those signs that you got better. As long as I'm consistent, it really doesn't matter what your sign convention is, but I agree. This guy goes minus, this guy goes plus, because that's right-hand rule. What do you get for AB? 133.3, thank you. Kips of compression. So I'll list it on the member as a minus 133.3. And on and on and on and on and on. Enough of that one. You see how to get them. Darned if I know. I guessed it compressive. Okay. And when I saw moments about G, this guy here wanted to go against the right-hand rule, so we called him a minus tendency to roll. And this guess went positive tendency to roll. And when I moved that to the other side of the equation, the answer came out plus, meaning only that the arrowhead is correct. That's not the sign that we're going to use, for our deflections. All right, I'm assuming you can get the rest of them. Next, here is the structure. Phooey. And I asked you for D horizontal, and therefore I want D horizontal. I want to put a unit load on the structure. I think I'll start doing a kip. It looks better. And this is 15 and 20, 20, 20. And A, B, C, D, E, F, G, H. Here's my name list. Marino, how do you suggest I solve for the forces in those members? Hang on a second. I got to tell you which guy was a roller and which was a pin. I didn't have to tell you that before. There's a pin over here and a roller over there. There's a pin here and a roller here. And the reason that I saw I'm going to have to cough up one of them a pin, one of them a roller, there wasn't any horizontal load on it before, so I didn't care which one was rollered. Now I do. The question was, how am I going to solve for the forces in those members? What do I have to do first? Pavlicek, what do you got to do first? Maybe this was the problem on that quiz. Roberts, what do I got to do first? You know you're going to be next, so you better plan on it. Roberts didn't think he was next. So, well, okay, that's what I got to do, but I mean, what are you doing? Why are you doing that? You're solving for the reactions. You can't find the force in a member, you solve for the reactions. You may be the only person in here that knows how to do this. So can I ask you about which point would you sum moments? A, did you say? H? H would be fine. There's an unknown reaction at H called H vertical. There's an unknown force here called H horizontal. There's an unknown force here called E vertical. You can sum moments about H is equal to 0 is equal to minus 1 kip times his moment arm is 15 feet plus E vertical times his moment arm 60 feet and solve for E vertical. I'm just going to put a circle around it. You then sum forces vertical and you can solve for this guy. You then sum forces horizontal and this guy is a 1. And you get the forces in the members just like you did on everything else. First, you can cut these two members. You can cut out that joint. That 1 will be a 1. It'll be a positive because it's tension. This guy will be a 0. Since this guy is a 0, there can't be any up and down force here because when you cut this joint out, if you sum forces vertical and there's a number in there, this guy won't take care of it, so this has to be a 0. If that's a 0, yes, sir.
Why is it 0 if you have that H vertical?
Okay, well, here, no, if I went too fast, let me just do this. First off,
Oh, never mind.
Yeah, that can't be a 0.
no. You're right. No, it can't. It's not a 0. I'm sorry. You're absolutely right. I thought there was no reaction. I thought it all went right here. Give me H vertical right quick. What is,
Fourth down,
how much?
1/4 going down.
Oh, going down. Wrong direction for this, and 1/4. Thank you. That's what I was looking for. It could turn out to be a 4th, huh? Right on the money? 2.5. Okay, now then, here we go. 0.25. This guy right here sitting at a known slope of 15 by 20 by 25. You can sum forces vertical and solve for this force. Knowing this force, you can sum forces horizontal and you can solve for this force. And then you could come in here and use method of sections or method of joints. Nothing new there. Here's the final answer. The final answer is this guy right here times how far, you'll notice I'm changing diagrams, times how far this guy moved to the right. The deflection at D horizontal due to the real loads. The 1 times the deflection at D horizontal due to the real loads is equal to the sum of all of the forces due to the Q loads. That's these guys here. This is the Q system. Times the forces due to the P loads. Here's your P system. Times the what? Times the length divided by A, E. We're going to feed me this stuff a bit at a time, aren't you? When you add that up, there's your solution for how far that point moves to the right. What do you use it for? You'll use it when this structure right here has another support in the middle, and you can't solve for the forces in the structure to design it. You'll take that reaction out and you'll ask how far he deflects down. You'll do that by putting a unit load at the point that you're interested in the answer, in the direction you're interested in the answer, and solve for the deflection. You'll get rid of it by coming and putting a reaction up where that point was removed, or where that reaction was removed. All right. I want an influence line for the moment at B. This is point A, here's point B, here's point C. Point A is 5 feet over, and point C is 10 feet over. To get the influence line, I'll give you a hint. I hope you know this by now. You take it home and you kink it. 45 degrees. And if this dimension is 10, what is this dimension? And then you come and you put it back where it came from. That means this little piece right here, you stick it back in the wall, and that is its influence line. Well, Gitman has to pay something here. Influence line for the moment at B. Here's the influence line for the shear at B. Turn it in. Dang, Lightfoot? Where's Lightfoot? It's no wonder you're late. Must have taken you days to draw all this stuff. Would you use AutoCAD or?